Hello everybody, this is Mr. Koker and I'll be covering Module 8. Module 8 is the gas laws. This is a reference to the song Jumping Jack Flash. It's a gas, 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 which is a Rolling Stones song. So Cheryl has given us this little reference here. Remember, Module 8 gas laws will involve quite a bit of algebra. You may remember the algebra from Chem 1 that goes along with the gas laws. As we do the large number of gas law example problems, I will be going through them fairly quickly, and you'll be able to slow it down if you need to, or stop it and pause it if you need to along the way because of the way the presentation is made. So keep that in mind if you need to write down the problems. I will tell you that Cheryl, when she does her math for the gas laws, what she prefers to do is rearrange the equations algebraically and solve for the missing variable as a set of variables and then plug in the numbers and get the answer. Some of you may prefer to plug the numbers in and then rearrange the numbers to solve for the missing variable. Either way is fine. So whatever you're more comfortable with the algebra, whether you do it your own way or Cheryl's way, as long as you watch your units and watch your sig figs and make sure you do the algebra rules properly, you should be fine on these. There's quite a few example problems in the Mastering Chemistry, in the class supplement, and also the post lab, so there'll be a lot of chances to practice this. So without further ado, let's go ahead with Module 8, the gas laws. Just a quick reminder of some properties of gases. These go back to Module 2. We know that gases are very, very tiny particles, atoms, molecules that move at high speeds, hundreds of meters per second, so multiple football fields of distance per second. Of course, they bounce around off of each other, so they don't actually move that far away from us, but they are traveling at very, very high speeds in various random directions. They travel in straight lines and hit things and then bounce off. We assume that the attractive forces that gases have between each other are negligible. They're very, very tiny, and that's because gases tend to not have very strong attractions because they're nonpolar usually, and also because of the large distances between them. They tend to not be very attracted to each other. So to make the math much simpler, we just assume that the gases have no attractive forces at all. Like I said before, gas molecules are very far apart, which means they're not going to be very attracted to each other, and that they're going to have very low density. You can pass your hand right through the air without hitting very many gas molecules and without having very much air resistance. The gas molecules are very far apart. It's about 99.9% empty space and only 0.1% of space that is filled by the gas molecules in a typical gas. When it comes to the temperature of the gas, the temperature, when you measure it in kelvins, will be proportional to the average kinetic energy. Gas molecules in a sample of gas are going to have a variety of kinetic energies, but the average kinetic energy is proportional to Kelvin temperature. So when you heat up a gas to a higher temperature, you're going to raise the motion energy of the gas molecules. Finally, these gas particles that are moving rapidly in straight lines and bouncing off of each other, and when they bounce off the walls of their container, they exert pressure. Under pressure, the pressure exerted by gases is when they hit the walls of their container. They give a little push on the wall every time they hit and bounce off, and that little push is called pressure. When you add up all of the gas molecules hitting the walls at very high rates of speeds, even though they're very tiny, they can add up to quite a bit of force over the area of the surface area of the container. So that's the pressure. We call the pressure capital P for short. When you speed up the molecules and make the collisions more energetic, then the pressure will go up. So that's a connection between pressure and temperature. We measure the pressure in two possible units that you'll see in this module. Atmospheres, abbreviated ATM. An atmosphere is kind of average air pressure at sea level, or millimeters of mercury. Some of the early instruments for measuring pressure actually measured pressure as how high it would push mercury up a tube. In fact, the first barometer for measuring air pressure was invented by Torricelli, and so the millimeter of mercury, mmHg, is sometimes called a torr after Torricelli. So standard pressure is 1 atmosphere. So anytime you see in an algebra problem that something is changing from or to standard pressure, just remember that's 1 atmosphere, or if you happen to be in millimeters of mercury, that's 760 millimeters of mercury. Of course, when two things are equal, you can always make a conversion factor out of it. So this could be a conversion factor, 1 atmosphere over 760 millimeters of mercury, or 760 millimeters of mercury over 1 atmosphere. The other properties of gas that we are going to be using in our gas law problems are volume V, usually measured in milliliters. Occasionally you'll see it in milliliters, but usually it's measured in liters. Temperature T, always measured in kelvins. Underline kelvins, kelvins, kelvins. You've got to convert Celsius to kelvins or the math problems don't work. Kelvin is found by taking Celsius plus 273. So don't forget, always convert your Celsius to Kelvin. Standard temperature. So together, standard temperature and standard pressure is sometimes abbreviated STP, standard temperature and pressure. Standard pressure, remember, was 1 atmosphere. Standard temperature is 0 Celsius, but of course we always change to kelvins, 273 kelvins. And finally, the amount of the gas. The amount of the gas in the gas law problems will be given the symbol N, which is actually how many moles of gas it is. So if the problem gives you grams, convert it to moles by dividing by the molar mass. If we think about how pressure can be affected by various properties, we know that going higher up a mountain or flying in an airplane at a higher altitude does lower the air pressure. The air is thinner the higher up in the atmosphere you go, and fewer collisions exert less pressure. Air pressure decreases as temperature decreases, and so slowing down the molecules means less energetic collisions. And finally, barometric pressure. Sometimes we measure the pressure of a gas in a container. Sometimes we measure the pressure of the air in the room or the air outside. That's called barometric pressure when you measure air pressure. It's actually because air has weight. And when you have 60 miles of air between the ground and outer space, all that air stacked up above us with gravity pulling it downward does create a degree of weight. Now, because air is a fluid, we don't just feel that weight on the top of our heads, but rather we feel it from all directions because air is bumping into us from the top, the bottom, and the sides. Now, most of our gas law problems are going to be based on the relationships discovered by these 4 guys. They are Robert Boyle, Jacques Charles. Sherrill gives credit to Gay-Lussac, and that is sometimes found in textbooks and so forth, but I believe from my research that I've looked some things up about Gay-Lussac's law, that really Gay-Lussac really did not discover this particular gas law, and that it might be more appropriately called Amonton's law, but really it doesn't matter who we call it, but just to give credit where credit is due, Amonton's law might be a better term for this one, but for Cheryl's sake here we'll call it Gay-Lussac's law. And finally, Avogadro's law. Same Avogadro that has the 6.02 times 10 to the 23rd number named after him. Starting with Boyle's law, Boyle measured the effect of changing volume on pressure. So similar to the little thing we see here in the bottom with the piston that goes up and down in the cylinder, If you change the volume, it will change the pressure. If you crowd the molecules closer together in a smaller volume, they're going to hit the walls more often and with more collisions per surface area, and so the pressure will go up. And so he found that pressure and volume are inversely related. When one goes up, the other goes down. But one effect of that mathematically is that when you multiply pressure and volume, you'll always get the same number. So if the volume is 4 liters and the pressure is 1 atmosphere, if you have the volume to 2 liters, you will double the pressure to 2 atmospheres. Remember, they're inversely related. 4 times 1 is 4, 2 times 2 is 4, so P1V1 equals P2V2. Of course, this will work if you hold the temperature and moles or amount of gas constant. So in other words, if it's a contained gas and you're not putting any more in, taking any out, and you're not letting the temperature change, you can always use Boyle's law, P1V1 equals P2V2. Jacques Charles's law, V1 over T1 equals V2 over T2. This is when pressure in moles are held constant. So once again, we have a constant amount of gas, but we are holding it at constant pressure. We will find that raising the temperature raises the volume, and lowering the temperature lowers the volume. In fact, it is directly related, but only directly related if we do Kelvin temperatures. Do not attempt this with Celsius temperatures. Okay, Gay-Lussac's law is very similar to Charles's law, except we hold volume in moles constant, and we see the effect of pressure on changing the temperature. So when we change the temperature, what does it do to the pressure? We find again it's directly related. As one goes up, the other goes up. Raising the temperature makes more energetic collisions, raises the pressure. If you make sure the temperature is in kelvins, the pressure will be proportional. And finally, Avogadro's law. Avogadro's law relates the number of moles to the volume. And so if the pressure and temperature are held constant, twice as many molecules, double the moles, should need twice as much space, double the volume. V1 over N1 equals V2 over N2. So these 4 gas laws can be used to solve a variety of algebra problems. Instead of trying to remember all 4, if we put all 4 together into a combined gas law, we can get P1V1 over N1T1 equals P2V2 over N2T2, with 1 being the initial conditions and 2 being the final conditions. Now you might think, why would I want such a complicated equation? Well, because all you need is this one equation, and if you have the moles and the temperature constant, remember you can take out the N1 T1 N2 T2 if they're the same on both sides. So in other words, if moles and temperature are constant, the combined gas law simply simplifies into Boyle's law, P1V1 equals P2V2. Likewise, if you hold the pressure and the moles constant, V1 over T1 equals V2 over T2, and you have Charles's law. Holding volume and moles constant, P1 over T1 equals P2 over T2, you get Gay-Lussac or Emonton's law. And then I think you see where this is going. If the pressure and temperature are constant, you have Avogadro's law, V1 over N1 equals V2 over N2. So really just this combined gas law is all you need, and then you just take out or remove any variables that aren't really changing. So they're really not variables, they're constants. So you just take them out of the equation, and you've got a simplified gas law. So just remembering the one combined gas law can get you most of these algebra problems. Just simplify it to include only the units or only the properties that are changing. So let's take a look at the combined gas law and the effect the combined gas law would have qualitatively on some of the properties if we change some of the other properties. And so for this particular slide, we're looking at changing certain properties and asking ourselves what would happen to the other properties. There are 2 ways to look at these questions. You can look at them from the standpoint of the combined gas law and thinking about it mathematically according to the equation. Or you can also think about the motion of the molecules and how they collide with the walls of the container and try to reason it out that way. Probably your safest bet would be do it both ways. Make sure you get the same answer both ways. So we have, to start with here, we have a picture showing an initial volume, and then either A or B. Would the volume get smaller, A, or would the volume get larger, B, if we, number one, decrease the pressure? Well, according to Boyle's law, when pressure decreases, volume increases, and so we should be letter B, where the volume is larger than it is initially. Notice that if you increase the volume, you spread the molecules out more, so the pressure should go down. If we increase the pressure, if we push harder on the plunger there, the piston, if we push it down with more pressure, then we should lower the volume, and it's because pressure and volume have inversely relationships there. Let's try completing these sentences with either the word increases or decreases. A, what does pressure do when volume decreases? If we decrease the volume, if we go from initial to letter A, then the pressure is going to go up because the molecules are bouncing around in a smaller size container, and so they're going to have more pressure on the walls of the container, so pressure increases. How about when temperature decreases, volume does what? Charles' law says temperature and volume are directly related, so in this case, temperature decreases, volume should decrease. What does pressure do when volume changes from 12 to 24? So we're doubling the volume, we're increasing the volume, kind of like going from initial to B. Spreading the molecules out in a larger volume means pressure goes down. So Boyle's law, pressure and volume are inversely related. And finally D, another Charles' law question. What does volume do when temperature changes from 15 to 45 Celsius? Of course, we would never do the math in Celsius, we'd do it in kelvins, but the temperature is rising. Molecules are speeding up, they're hitting the walls harder, they're pushing the walls back. So in a container where the volume is able to change, the volume should go up. So if you think about taking a balloon in from the cold into a warm room from the cold outside, then the volume should go up. The balloon should get larger. Let's check our answers. 1 was B, 2 was A, that's what we said it should be. Pressure increases when volume decreases. When temperature decreases, volume decreases. Pressure decreases when volume increases, and volume increases when temperature increases. So that's doing it with words. Now let's think about what we would do if we had numbers. This is Cheryl's suggestion. If you give an algebra problem with a series of numbers in it to help keep it organized, you should probably set yourself up a little list, a data table of what you know and what you want to find out. So first of all, put down what you know. If your temperatures are in Celsius, make sure they change to kelvins. All your other units need to match. So in other words, if V1 is milliliters and V2 is liters, you want to convert them so they're both the same unit. So just make sure all your units match. They're in the same unit on both sides of the equation. Then manipulate your combined gas law. So once again, you can either reorganize the combined gas law to solve for the unknown, then plug in your numbers and solve it, or you can plug in your numbers and then move numbers around to solve for the missing variable. But here's where your algebra skills are going to come in handy. You plug in your data with its units. So if you keep your units with your numbers as you're plugging it in, and you're doing this work on scratch paper, then your units, how they cancel out, will help you with the units that you want to have in your answer. And finally, you get your answer. Make sure when you get your answer, you double check what your proper units should be, and you also double check your sig figs. Since most gas law problems are going to be multiplying and dividing, we should be using the weakest link principle here with sig figs. Excuse me, just had a sneezer. You should be using the the effect of sig figs and also of units. For sig figs, you should be using the effect that the least sig figs should determine the sig figs in the answer. Okay, here's our first math problem. Freon 12, used in refrigerators and air conditioners. What would be the new volume in liters of an 8-liter sample of Freon gas if it starts out at a pressure of 550 millimeters of mercury and the pressure changes to 2200 millimeters of mercury? We're holding temperature and moles constant, so we should be doing a Boyle's Law problem here. So here's our data table of what we know and what we want to know. We've got our pressure 1 and our pressure 2. We've got our volume 1, and our unknown is volume 2. N1 and N2 are the same, T1 and T2 are the same, so those should cancel out since they're constants. So really what we have here with N1 and T1 not needed is P1 V1 equals P2 V2. Boyle's Law. If we reorganize it to solve for the missing variable V2, we get V1 times P1 over P2. Plug in our numbers, 8 liters times 550 millimeters of mercury over 2200 millimeters of mercury. And millimeters of mercury, notice, cancels out. And so what we're doing here is we're multiplying the pressure by 4, which should cut the volume by 1/4. So 1/4 of 8 is 2 liters. Notice we keep 2 sig figs here. Okay, here's another example. Oxygen at a volume of 420 milliliters and a temperature of 18 Celsius. So red flag there, make sure you change that to kelvins. At what temperature? In Celsius. So we're going to get our answer in kelvins and have to change it back to Celsius. Will the volume be if the oxygen's new volume is 640 milliliters? Pressure in moles are constant, so we're looking at a Charles's Law problem here. So P and N are constant. V1 is 420, V2 is 640, T1 is 18 plus 273, 291, T2 is watt. And so if we take pressure in moles out of the relationship, then we have V1 over T1 equals V2 over T2. Solving for T2, cross multiplying is actually allowable here. V1 T1 equals V2 T2, and then divide both sides by V1, and we get T2 equal to T1 times V2 over V1. So plug in our numbers now with units and solve it. 291 times 640 divided by 420. Notice the milliliters cancel. Gives us an answer of 443 Kelvin, but read the question, read the question, read the question. It wants Celsius. So we have to subtract 273 to get Celsius. We get 170 Celsius. The decimal just means that we're keeping 3 sig figs. Another example, this one with moles and volume in it. So this would be an Avogadro law problem. 0.75 moles and occupies a volume of 1.5 liters. What will the volume be if you have 1.2 moles and you keep the temperature and pressure the same? So here we have N1, V1, N2, and V2. V2s are unknown. Pressure and temperature go away because they're constants. So we get V1 over N1 equals V2 over N2. Cross multiply again, and get your V2 by itself. V1 times N2 over N1. Plug in your data. 1.5 liters times 1.2 moles over 0.75 moles. Moles cancel out. Gives us 2.4 liters, 2 sig figs. Another quick example. Gas has a volume of 675 milliliters and temperature of 35 Celsius and a pressure of 0.850 atmospheres. What's the volume at negative 95 Celsius and a pressure of 802 millimeters of mercury? Now notice in this case we only really have one constant. So this is not any of the 4 gas laws. This actually is, if we take the combined gas law, P1 V1 over N1 T1, and just take out the N1 and N2, then we'll get our answer based on the P1 V1 over T1 relationship. So P1 is 0.850 atmospheres, but I want to put the two pressures in the same unit, so I think I'll change that one to millimeters of mercury by multiplying by 760. Remember, 760 millimeters of mercury over 1 atmosphere makes a good conversion factor. So P1, 646 millimeters mercury, so the units match with the P2, 802 millimeters mercury. V1 is 675 milliliters, so my answer for volume 2 will also be milliliters. N1, N2, those cancel out. T1, 35 Celsius, 308 Kelvin. T2, negative 95 Celsius, 178 Kelvin. So, if we manipulate the combined gas law, we get V2 equal to P1 V1 T2 over T1 P2. Watch your subscripts here because you got to make sure the proper numbers go on top and bottom. Once we plug it in, we get 646 millimeters mercury times 675 milliliters times 178 Kelvin over 308 Kelvin and over 802 millimeters mercury. Millimeters mercury and kelvins cancel out, so we end up with a ratio of 314 milliliters. Now, besides those gas laws, there is one more. It's called Dalton's law. John Dalton, same guy that did the atomic theory and also the law of multiple proportions, but he also worked with gases, and he found a relationship between the pressures of each individual gas in a mixture and the total pressure. It's actually a very easy relationship because you can assume that each gas in a mixture is going to act like it's the only one in the mixture, and so the pressure each gas exerts has no effect on the pressure the other gases exert. And so each gas's pressure is called its partial pressure, and all you have to do is add those up, sum them up, and you'll get the total pressure in the container. So it ends up looking like P total, PT, P total equals the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas plus however many gases there are. So it's very simple. We could apply it to the pressure of a gas in, say, a scuba diver's dive tank. Let's say that the dive tank has 3 gases in it. The first one is nitrogen, and there's 2,850 millimeters of mercury exerted by the nitrogen, 2,440 millimeters of mercury exerted by the oxygen in the tank, and 750 millimeters of mercury exerted by the helium in the tank. And so we want to know, with those 3 gases all pushing on the sides of the tank, what is the total pressure? 2850 plus 2440 plus 750 would be 6,040 millimeters of mercury. So all you have to do is add up the numbers. So I'm sure you're hoping there's lots and lots of these example problems. Now what would we do if some of these pressures were atmospheres and the others were millimeters of mercury? Well, all we would do is convert them all to the same unit using our conversion factors. Here's a little more practice. A sample of helium has volume of 120 milliliters and a pressure of 850 millimeters mercury. What's the new volume if the pressure is changed to 425 millimeters mercury? If you're good at math, you might notice we cut the pressure in half. And according to Boyle's law, if you cut the pressure in half, you should double the volume. Let's see if that's true. P1 850, V1 120, P2 425, V2 is what? Now, N1 and T1 cancel out here, so we end up with that relationship that V2 is V1 times P1 over P2. 120 milliliters times 850 millimeters mercury over 425 millimeters mercury cancel out, we get 240 milliliters. Yes, we did double the volume. Gas has a pressure of 645 torr at 128 Celsius. What's the temperature in Celsius if the pressure increases to 1140 torr? Notice we're using torr here, which is the same basic unit as millimeters mercury. And moles and volume are constant, so this is a pressure-temperature relationship. Got our P1, our T1, our P2, and our T2. And we just need to use the Amonton or Gay-Lussac's law. P1 over T1 equals P2 over T2. Solve for T2, plug in our numbers, 401 Kelvin times 1140 torr divided by 645 torr. Torr cancels out, 709. She left off the unit here. This will be 709 kelvins. Kelvins minus 273 is 436 Celsius. Let's take a look at another problem. A sample of oxygen gas has a volume of 12 liters at 600 millimeters of mercury. What is the new pressure when the volume changes to 36 liters? It triples. Temperature in moles constant here. So we have a pressure volume. This is Boyle's law. Pressure 1, P2 is unknown, V1, V2, plug it in. P2 equals P1 times V1 over V2, 600 millimeters of mercury times 12 liters over 36 liters. If we triple the volume, we should cut the pressure by a third of its original value, so we end up at 200 millimeters of mercury. The decimal shows us we have 3 sig figs. Don't forget units, don't forget sig figs. Another example problem about a balloon. And of course, a balloon has variable volume. 785 milliliters at 21 Celsius. Temperature drops to 0. What's the new volume of the balloon? Of course, this could never be done in Celsius because you'd be dividing by 0. But you can do it in kelvins. We know V1. We don't know V2. We know T1 in Celsius. Convert it to kelvins. We know T2 in Celsius. Convert it to kelvins. V1 over T1 equals V2 over T2. Do your cross multiplying, get your V2 by itself, V1 times T2 over T1, 785 milliliters times 273 Kelvin over 294 Kelvin. Kelvins cancel, 729 milliliters. Another example, a gas has a pressure of 2 atmospheres at 18 Celsius. What's the new pressure when the temperature is 62 Celsius? Set up our data table. P1 we know, P2 we don't, T1 we know, we change it to kelvins. T2 we know, we change it to kelvins. 291 and 335. Plug them in. P2 is 2 atmospheres times 335 Kelvin over 291 Kelvin. We get 2.3 atmospheres, 2 sig figs. Weakest link was P1, 2.0 atmospheres. Here's an oxygen problem. Oxygen gas, a volume of 420 milliliters, temperature of 18 Celsius. What's our temperature when the volume is 640 milliliters? Pressure in moles constant. T2 is T1 times V2 over V1. 291 Kelvin times 640 milliliters over 420 milliliters. 443 kelvins. Milliliters cancel. Minus 273 is 170 degrees Celsius. I think she should have put a decimal. No, we actually only have 2 sig figs here. So yes, she is correct. 170 degrees Celsius. Only 2 sig figs. And finally, our last slide. A sample of helium gas has a volume of 0.180 liters, pressure of 0.800 atmospheres, and a temperature of 29 Celsius. What's the temperature in Celsius when its volume is 90 milliliters and a pressure of 3.20 atmospheres? This is one with 3 different properties: pressure, volume, and temperature. 0.8 atmospheres, 3.2 atmospheres are 2 pressures. One of our volumes is liters, one of them is milliliters, so we should change them both to, let's say, liter or milliliters. 0.810 liters times 1,000 milliliters over 1 liter is 180 milliliters. V2 is 90 milliliters. T1 is 302 kelvins. Change it to kelvins. If we drop in out of the combined gas law, we get P1 V1 over T1 equals P2 V2 over T2. Reorganize it. T2 should be 302 Kelvin times 3.2 atmospheres times 90 milliliters divided by 0.800 atmospheres and divided by 180 milliliters. Atmospheres cancels, milliliters cancel, we end up with 604 Kelvin. So change it to Celsius, we get 604 minus 273 equals 331 degrees Celsius. So as you can see, it's a lot of algebra to this module, and just be aware of sig figs and units and doing your algebra properly and using the combined gas law and occasionally using Dalton's law. And I think that if you practice it on your Mastering Chemistry, practice it on your class supplement, practice it on your post-lab, ask Mr. Koker any questions if you have any questions about the algebra and how to do it. And you should get pretty good at these before Friday's quiz. Hopefully getting a lot of high scores on Friday's quiz, because all this is really just a bunch of algebra. So thank you very much, guys, and good luck.